there we go. Okay, so exponential functions. There's a couple of rules we need to go over. First of all, an exponential function is not the same as a quadratic or a linear function. This is an entirely new function that we're learning about. The equation of an exponential function, we'll call this like its standard form, is written like this. A times b to the power of x is equal to y. Okay? Now, a stands for the initial value. In other words, really when x is 0, what is our a value? Okay? And that's also known as the y-intercept. Okay? We'll keep that in mind. That's our y-intercept. B, on the other hand, is our growth or decay rate, depending if we have an exponential growth or if we have exponential decay. And just to give you an idea of both of those here, we'll make a quick graph. A growth rate does something like this. It cuts through our y, and it goes up like this. So this is exponential growth, or a rough sketch of it. And exponential decay does kind of the opposite. Whoops. Does not touch the x-axis, though. Let's try that again. Okay, so here's our decay. Now, what's important about this is that exponential growth and decay will never touch our x-axis. In other words, that's called the horizontal asymptote. And what that means is it will constantly get closer and closer and closer to the x-axis, but it'll actually have no x-intercepts, or exponential functions. So, I want you to think of this idea. Let's say that you, okay, whoops, is it your A? He's walking towards functions, but he walks halfway. So from where he is, he walks halfway. And then he decides from there to walk halfway again. And then he decides to walk halfway again. Because he continues to walk a half every time, he never actually reaches functions. He'll get closer and closer and closer, but he'll never touch it because he always walks a half of the way. It's the same idea with an asymptote. We get closer and closer and closer, but we'll never actually touch that line. So keep that in mind for exponential functions. Okay? Now there's a couple restrictions we need to talk about. When b is greater than 1, we have a growth rate. So we'll have our red-looking exponential function here. And when b is between 0 and 1, we'll have a decay rate. So this is the green-looking one. This is a decay rate. And we do not have an exponential function if b cannot be equal to 1, and it must be greater than 0. Okay? So if we have a negative value for b, we're not dealing with our exponential function. And if it's 1, it's not exponential because 1 to the power of anything is 1. It never changes. It won't have a growth pattern or a decay pattern like this. Okay? So, first of all, we have a table here of xy values. On the table, we're going to talk about how we can decide if something is exponential, quadratic, or linear. How would I know if something is linear from a table? First differences. Okay? So let's quickly do a first differences here. 6 minus 2 gives us 18 minus 6, 12. 54 minus 18, anyone know? That's going to be 20, 32, 6. And then 162, subtract 54, it's going to give us 108. Okay? First differences, are they all the same? So, is this linear? No. How do we find out if something is quadratic? Okay, so we take these differences. 12 subtract 4. Beautiful. 36 subtract 12. Excellent. 108. Whoops. Subtract 36. A little tougher. 40, 60, 72. Is it 72? 72. Our second difference is the same. No. So is this linear or quadratic? Neither. Okay. But what we're going to do is, I'll call it first ratio, but really it's just taking the ratio of the y values. And what I mean by that is we take the first number, and a ratio uses what operation? Sometimes multiplication. It's usually written like a fraction, which is what? Division. So we're going to take the ratios. 6 divided by 2 gives us what? 3. 18 divided by 6 gives us, okay, 54 divided by 18, Are you sure? Did you try it on your calculator? You're the best. And 162 divide 54? 3. Okay. This is very important. This ratio is our B. Okay? Our B is 3. So is this growth or decay? Growth. Why is it growth? It's greater than 1. Also, the numbers are going up. Makes sense, right? It's a growth rate. Our A value, we said, is the what? Y-intercept. Looking at this table, how can I find my A value? Y-intercepts are when what is 0? Not when y is 0. When x is 0. So what is our A value? 2. So in this, our A value equals 2. I can already build my exponential function just from that table. Y is equal to, remember it's A times B to the power of x. Our A is what value? Yep. 2 times 3 to the power of x. That's it. There's our exponential function. We have our initial start and we have our growth rate. Just looking at that table. Okay? We've already figured it out. So, how do we graph that? Okay. So, we have our equation now. We said it was y, our A value was 2, and our B value, our growth rate, happened to be a value of 3. We need to graph this. So we're going to use a table, and we know how to graph using a table by just putting in values along our graph, our x-axis. We're going to start at the y-intercept. So we're going to plug 0 into the equation to help us find this. Okay? So we'll do each step here. When x is equal to 0, our equation reads y is equal to 2 times 3 to the power of 0. What's 3 to the power of 0? 1 times 2 is 2. So our y-intercept is at 0 and 2. That makes sense, right? I'm pretty sure that was the exact value we had before. Let's go up another one. Value of 1. When x equals 1, y is equal to 2 times 3 to the power of 1. What is 3 to the 1? 3 times 2. Our y value is 6. So our next coordinate is 1 and 6. I'd say it's about there. When x equals 2. Y equals... Oh, good. What's 3 to the power of 2? 9 times 2. Beautiful. So our next value here is 18. And this is going to continue to grow. Now let's continue it. 3. X to 3, what is it going to equal? It is 54. How did you remember that? Yeah, the ratio. We really just got to multiply that value up by 3 again, right? So our next one is 54, which is way up here. So you notice this is really starting to grow. An exponential grows by more and more every single time. What is the next value? Anyone know? It is 162 when it's 4. Okay, and you could have done that, A, by knowing that these are going to multiply by 3, or you could have looked at our table from the other side, or you could have continued putting in all the values into our equation. Okay, so 162, that's not even a value on this chart. I can't even keep up with it, okay? So it's going to really start to grow. Now, what I do want to show you, though, is kind of the opposite idea. Let's go to -1 and figure out what happens here. Okay, so we'll put it into our equation. When x equals -1, we have y is equal to 2 times 3 to the -1. How can I simplify 3 to the -1? That's right, so 2 times a third. How do I do that? Multiply. It is 2 over 3. Is that 1 or is that less than 1? That's less than 1, right? So it's not quite 0, but it is less than 1. All right, and let's try -2. So we have 2 over 3. Let's try -2. When x is -2, we have y is equal to 2 times, how do we simplify that negative? Okay. 1/3 to the power of 2. What's 1/3 squared? Yeah. Which is going to, in the end, what's it going to be, PJ? That's right. 2 over 9. So it's much smaller, getting closer to 0, but not quite 0. Okay. And if we wanted to go the other way, we're dividing by 3. What's 2 divided by 3? 2 over 3. Oh, sorry, not 2. 3. Right? 2 divided by 3 is 2/3. 2/3 divided by 3 is 2 over 9. So if we went up the other way, we divide by our ratio. And again, it'll never, and I'm not very good at drawing this, It'll never touch the x-axis. Okay? And if you notice, our values are identical from what we had before in this chart here. 2 to 162. And we just went backwards. Okay? So we have our growth rate and our decay rate. Okay. We have decay. We have a decay rate. We're going to see what this looks like by doing the same type of thing here. So, our y value is 2. This time we have a third, and it's going to be to the power of 0. What is 1/3 to the power of 0? 1 times 2 is 2. So, our y-intercept is identical. Okay? And that's because the a value is 2. So our y-intercept didn't change. Let's go in the same order when x is equal to 1. So, a third times 1, and then 2 times 1/3 will be 2 over 3. Does that seem familiar to you guys anywhere? What was that value before? That was the negative 1. Okay? X at 2. So, a third squared is going to be 1 over 9, which will give us 2 over 9, which is again was our negative 2. Okay, so let's plot these 2 points. A third is probably somewhere here. 2 over 9 is even closer. The next one's actually going to be, because when we're going down this way, we're actually dividing by 3. We're going to get with 2 over 27, which is going to be even smaller, but again, really hard to graph on this. Now, here's the tricky one. X equals negative 1. Y equals 2. A third to the negative 1. How do I make that positive?
3 over 1.
3 over 1, or just 3. 3 to the power of 1 is still 3, so that gives us 6. So it's almost like it's the opposite of before. So we did this by just multiplying by 3, which means the next value will be what? 18, that's right. So if you look at negative 1, we're at 6. And 2 is at 18. We have what's considered a decay rate. Getting closer and closer, but never actually touching.